kind of importance. We have this. We go till 1:15 or so. So that's good. So we have about an hour and 15 minutes. That's good. I think I can run through this and make this work. Well, what I want to talk about is for this lecture is cost models and cost model in studies for directed energy deposition parts, including repair. This is an extremely important commercial consideration because we can do so much more than just figure out what a price point would be for a part made using DED. For example, I imagine this hypothetical example that suppose we say, well, you know, we're paying so much money for feedstock for the metal powder, so why don't we develop our own metal powder that will be cheaper? And so a company could spend an extremely large amount of money, and so let's suppose hypothetically that they actually do make a cheap metal powder for DED. Well, without the value of the cost modeling, they could very well find out that even if they use this cheaper powder, it doesn't affect the cost of the part. And that's where the cost model comes in, and where the real value is because we can learn from the cost model where we need to be, where the low-lying fruit is, as it were. Where are the aspects of the processing that have a big impact on part cost? And let's start there and let's attack those rather than the feedstock. So, for example, I can tell you just immediately with nylon and powder bed fusion, which is sort of my long suit, that the cost of the powder is almost negligible, has a negligible effect on the cost of the part. The place where we save money on the cost of the part in polymer powder bed is by making the machine cheaper that fabricates the part, or by making more parts in a given period of time, that is to increase the production rate. And that's where all the effort is. It's all based on understanding the cost models. So let's see where we are with this. I already showed this plot that yesterday that showed the cost per piece, which is the number of pieces, and how additive can find a niche. But the question for this part of the talk is where does that horizontal additive manufactured line fall? If $100 for a 2 pound or a 1 kilogram part, if that's too expensive, what can we do to lower that cost? And that's where the modeling comes in. I want to mention, you know, typically what's done in additive manufacturing is it's relatively easy to calculate part cost in terms of the build itself, but there are a lot of other costs that go into the part. So there's pre-processing costs, there's post-processing costs, you know, associated with finishing and perhaps heat treatment. And what this shows, this is data from last year's Wohler's report, where they're actually looking at commercial data, not academic. And what they found is that pre-processing for metals is typically about 10% of the total cost of the part at the end of the day, and about the same for polymers. And post-processing for metals and polymers is also pretty close. And so what we find here is that about 2/3 of the cost of the part is the actual printing, the actual additive manufacturing. And what this does is it gives us a powerful tool, because what we can do is we can say whatever the printing cost is, I can sort of just multiply by 1.6, and that'll give me the total cost of the part. Now, because the pre-processing and post-processing cost is a little more difficult to get a handle on than the printing cost. So I'm going to focus on the printing cost, but appreciate that we can actually get the total cost by multiplying by a constant. Okay, there are a number of cost models. The one I'm presenting has 4 features to it, and it's a little bit complicated, but not horribly complicated. at least in principle, it's relatively simple. We have these four cost factors that come in, and this is for any manufacturing process. What we have is, of course, we have the feedstock costs. We have to buy the material that we're going to process. And again, this is true for any manufacturing process. Then the second is the equipment cost or the capital cost. So this is effectively the machine that does the fabrication. So for directed energy deposition, it would be the lens machine, the purchase of the lens machine. And so we would have that cost, and we have to figure out, if I run parts on that, you know, if we're in business and we don't want to lose money, I have to burden each part with a little bit of money, so that at the end of say 5 years or 10 years, when it's time to replace the lens machine, I have enough money in the bank to buy a new one, right? So that's what the permanent equipment cost is. And typically, you know, and this is generally the case for a lens machine. Typically, we won't buy a lens machine just to run one part and then put the machine aside. You know, we would use it to run many different kinds of parts over a very long period of time. And so while certain things may vary, the machine costs would be spread out over multiple jobs, as it were. And so that's the way we handle it in the cost model. There's also the tooling cost, which fortunately in additive manufacturing we don't worry about that, because we don't have tooling typically to have to deal with. Again, you can imagine you know, some rare cases where that would be the case. For example, if we had a sheet lamination machine with a cutting blade, you know, the blade would have to be replaced. So that would be considered a tooling cost. But for the most part, and certainly for DED, we don't really think of there being tooling costs to deal with. And then these first three in cost modeling are referred to as direct costs. So these are costs that are directly associated with doing the build or with the manufacturing of the part. The last one is the overhead or indirect costs. And this, you know, for those of you that maybe are in business, you know this better than I, is there's a lot, we have to have a lot of money available. And again, the only way we get money if we're manufacturing is the only way to get money is by selling parts. So that means if I need more money, I have to burden the part with more money, more cost. I have to increase the cost of the part in order to get more money to do these things. And so the examples of overhead costs, we'll talk about this in detail in a bit, but it's things like the building or the space where we do our additive manufacturing. We have to pay building rent every month, or the receptionist or the staff person that sits at the desk at the front and greets people when they come to visit, or the sales staff, or the office furniture. You know, these are all things that are important. They all cost money, and the only way I can get that money is by burdening the parts I'm selling with a higher cost. And so the overhead or the indirect costs they're not directly associated with making parts, but if we're going to be a profitable company, it has to be part of the equation. So they're included here. So let's look at these. There are a couple of models or rationales that we can use and this really has to do with how I distinguish the equipment from the tooling. So what I can do is this shows sort of the job shop or service bureau approach, where basically we say we're going to get an additive manufacturing machine, a DED machine, and we're going to basically take in jobs from outside and we'll build those parts and sell them to customers, and there has to be a steady stream of business for us to be profitable. So what we might do here, this is over time, so we might get an order for 2,000 parts, and then at some later point after we finish those, maybe there's a 10,000 part order that we run. Then maybe we get a little order for 250 parts of something else, and then maybe later 3,000 parts, right? So we have maybe over the course of some period of time, you know, we have multiple parts that are being run through the machine. If we were in a process, conventional process, like say injection molding or die casting, what we would have to do is for each one of these parts, we'd have to create a mold set or a die set or some tooling. And this tooling, don't worry about the fact that the tooling doesn't match the geometry of the part. This is just for illustration purposes. So for this, we might spend, say, $36,000 on a die set to make these parts, say we were die casting them. But then, once I finish those 2,000 parts, this die set really has no value, right? It's not good for anything else. I can't use this die set to create these parts, right? It can only make these parts. So typically what happens in the job shop, where there's tooling involved, is once they finish that job, they take the tooling and it just goes and sits in a corner of the space, and it's never used again, except maybe perhaps in the hopes that this customer might come back and say, well, I've used my 2,000 parts, I need another 2,000. Then we can pull the die set out and make more parts. So we don't, typically they don't throw the dies away, but at least for this string, this die set is no longer good for anything. And so what we would do is once we get this order for 10,000 parts, we'd make another die set that would fit this set, this part, and then we would run these parts. And then when we get to this 250, we might spend $25,000 on a die set for this and run 250 parts. And then again, maybe $42,000 we spend on a tool set for this. So that's the way it goes. And so what the issue though is for this die set, if I have $36,000 on 2,000 parts, that's, if I can do the math in my head, that's $18 per part. 36,000 divided by 2,000. That means that basically for every one of those 2,000 parts that I make, I have to assign $18 to that part plus some other stuff, but just to recover the tooling cost, right? So for this part, the tooling cost would be $18 per part. If I come over here to this one, where I have a $25,000 mold set and I only run 250 parts, that means I have to burden each part with $100, right, in order to cover the tooling cost. Because once I finish this run of 250 parts, I have to have enough money to take care of purchasing the die set, right? So that means it's $100 per part here. So this part, relative to the tooling cost, is much more expensive than this one because it's an expensive die set and it's only a few parts. Okay, so that's the way the tooling works. And again, for additive manufacturing, this line typically goes away. Now the equipment's a different story. Let's say we buy a machine that's $500,000. Typically what we do from a business perspective is we say we're going to use this machine for a certain period of time, not for a certain number of parts. And this so-called write-off time is could be 5 years, could be 10 years. In general manufacturing, let's say we buy a welder or a rolling mill, a big expensive piece of equipment, it could run for 20 or 30 years before having to be replaced. But basically we have to decide how often we want to replace the equipment, and what I have to do is I have to burden each of these parts with a piece of this $500,000 so that at the end of the write-off time, say 5 years, I have $500,000 in the bank so that I can buy another machine. Otherwise I go out of business. Okay, so that's sort of the way that the tooling separates itself from the equipment, because the tooling cost, I have to recoup all of this cost over the part run, whereas the machine cost I can spread out over multiple parts typically, at least in the service job shop service bureau model. So there's also this single part model. The single part model is suppose we're in business and we're the customer that purchased these 2,000 parts from a service bureau. So we go and we place an order for the 2,000 parts, and the part cost in metal is going to be $800 a part. Well, what we possibly could do is we could sit down and say, gosh, $800 a part is really expensive. perhaps what we could do ourselves is why don't we just buy ourselves a machine and sort of take it in-house and produce the parts ourselves. And this is based on, there's all kinds of variations of this thing, but what I'm working here is the extreme case of we're going to buy a machine, we're going to run our 2,000 parts, and then we're going to basically crash the machine. It's not going to be good for anything else. In that case, I might have tooling costs, but I also have to treat the equipment costs like tooling, because once I finish these 2,000 parts, I have no use for the machine, and I have no use for the tooling. So this can be a very expensive way to go, but certainly it's considerable, considering how the cost functions work. And certainly, certainly there are hundreds of examples in manufacturing of companies bringing the manufacturing in-house, and this is exactly what the scenario is. Okay. So now let's move to a slightly different topic. Everything ties together in the end. But we have to talk about time measures. There's two kinds of time measures when doing cost modeling. The first kind is the total time. It's relatively simple. It's just basically, it never stops. It's like whenever we start our business, the clock starts and it never stops. It runs 24 hours a day, 7 days a week. And there's certain cost factors that are based on round-the-clock running. For example, the building rent. It doesn't matter that we're not making parts, right? If I'm not making parts, I still have to pay the building rent, right? And so there are certain parts of the cost model that are based on total time, just total clicks of the clock, 24 hours a day, 7 days a week. But there's also productive time that enters into the equations. The productive time is time that's like I have a stopwatch, and when I start making parts, I start the stopwatch, and when I stop making parts, I stop the stopwatch. That's so-called productive time. So, for example, let's say we have a 40-hour work week. The total time would be 7 times 24 hours, right? Whereas the productive time would only be 40 hours. So that's the productive time only tracks while we're producing parts. Total time tracks all the time, no matter what. And so what we can do is, in the cost model I'm using, we can relate those two by it's not a very good name. It's called the load, or the load factor, but it's a time load, not a physical load. And what the load factor is simply the productive time divided by the total time. So if I give the example of a 40-hour work week, with a 40-hour work week, the productive time is 40 hours, but the work week, the total time is 24 times 7. So that gives me a load factor of 0.24. If I work my machines 24 hours a day, 7 days a week, round the clock, then the productive time and the total time would be the same, and I'd have a load of 1. Obviously, if I only worked 20 hours a week, then the load factor would be 0.12. Right? So the load factor can go from 0 to 1, where 1 is we're producing parts all the time, 7 days a week, and 0 is basically the machines are down and I'm not producing parts at all. Okay, so the load factor will enter into the equations as well. Okay, so let's look at these the four aspects of the cost model. I mentioned there was the feedstock or the material cost, there's the equipment cost, the tooling cost, and the overhead cost. So what we have here is basically what you have to appreciate is we have to have enough feedstock to completely produce the part, and there's sometimes feedstock doesn't become part of the part, and so we have to purchase enough to make the part. That includes the potential of having scrap or material loss. And I can't go to my feedstock supplier and say, look, I'm only able to use 80% of the material I'm buying from you, so why don't you give me a 20% discount? It doesn't work that way, right? You have to buy it whether the supplier doesn't care whether you use the feedstock judiciously or not. If you're going to buy it, you have to pay for it. And so that's the issue here. So what we can do is basically to come up with for a given additive manufacturing, but really in general any part, for that part, the question is what's the feedstock part of the part? What's that cost going to be? And the way we can get that is we start by talking about how much mass we need to create the part, which is simply going to be the density of the material times the total volume that I need to produce the part. That includes material loss. So we have the total volume here. This gives me the total mass of the part. The material cost then is the so-called material cost, which is, say, so many dollars per kilogram. I take the mass and multiply it by the mass cost of the part. So it's dollars per kilogram times kilograms gives me P and rho V, which is just the cost of, say, dollars. And I should mention that I'm assuming this is true worldwide, certainly in the United States. When we go to buy material, we buy it by the pound or by the per unit mass. So that's the reason the equations are built, based on the material cost. And in a bit, I'll talk about what the piece of ends or what the material cost is for certain kinds of additive manufacturing metals or materials. We'll look at those in just a bit. So, but typically, I guess the spoiler is typically for additive manufacturing feedstock, whether it's polymer or metal, typically sort of runs in the $30 to $60 per kilogram kind of price point. So, just so you know. Okay, so there's usually material loss, not so much in additive manufacturing, but there is some. The classic example I think of is PEEK polymer in powder bed. PEEK polymer, it's a very expensive polymer, and it degrades thermally very quickly, and so it can't be recycled. So if I'm doing a full chamber build with PEEK material, a typical part versus part cake ratio is typically the full chamber build. Maybe we can fill about 20% of the chamber up with part, and then the rest is just feedstock, same with powder bed. So what that means then is that if I'm going to charge fully the machine to do a full chamber build in PEEK material, it turns out that the material cost is about $40,000, or at least it was at one point. It may still be. But if I only use 20% of the material, that means that I'm using $40,000 times 0.2, which I guess is $8,000 of that material turns into part, and the other $32,000 gets thrown in the trash can when I'm done. But I still got to pay $40,000 in order to do the build. So anyway, so scrap can be a factor in additive. Not tooling, not so much, but the scrap, yes. And so what we do is we typically have this parameter called the scrap factor, which is the fraction of the total material volume that's lost to scrap. That is, that can't be used. So in this case, the total volume is the volume of the part, it's the volume of the scrap. And what I can do is, to get this scrap factor, if I divide this equation through by the total volume, I have the fraction of the part, the fraction of the total volume that is part, plus this term, the volume of scrap over the total. This is indeed the value F, the scrap fraction. And so what I have is 1 is equal to the part volume over the total volume times the scrap factor. And if we solve this out, eventually I can write my total volume here, which I need to know, is going to be the volume of the part I'm making, which I also can figure out because I've designed the part. And so what I can do is, if I know the scrap factor, I can use this equation to take what I can calculate, the part volume, and convert it into the total volume that I need in this equation to actually calculate the feedstock cost that's needed. And so what that looks like at the end of the day is that the material cost for one part is going to be this the cost of the material per pound or kilogram times the density times the volume the total volume of part divided by this 1 minus F. And so obviously you can see that if F is small, if F is large, this number gets very small and my material cost shoots up. If I have a lot of scrap, my material cost shoots up. If I have very little or no scrap, then it sort of minimizes the material cost, right? Anyway, so we have this, and again, what I'm doing is I'm going to calculate all these costs based on a part, not based on a production run or anything else. It's based on a given part. Okay, let's look at the equipment cost, again, on a per part basis. So again, as I mentioned, we were going to assume that I buy an expensive piece of equipment, I use it for a certain period of time, say 5 years, and then I get rid of it and I buy a new machine. So it's sort of depreciated, and presumably would be over many different part runs. So what we can do is the following. I can take the, I can get this number by taking the cost of the equipment, C sub C, which would again, say for a DED machine, what would it be? Maybe $700,000 or something like that, perhaps. And then I divide it by the lifetime, which is this T sub WO, which is the write-off time. And again, it would typically be 5 years, 10 years, depending on the business model. But so this tells me the depreciation. I have to get so many dollars per year out of my part production in order to have enough money to buy a new machine at the end of the write-off time. And so what we do is I can do the following. It turns out that the equipment cost is easy. The write-off time is actually a total time because it's going to be 5 years of continuous time. But yet, what I want to do in order to get at the how I burden a part, I always have to convert back into productive time. So the way we do that is I effectively can just do kind of a lever rule kind of analysis where this is the cost per total time. If I multiply by total time and divide by productive time, the total times cancel, and then I have the cost of the equipment on a per productive time basis. And the total time over the productive time is just 1 over the load, because the load is my productive time over total time. So I can multiply then by 1 over the load, and so this becomes the equipment cost on a productive time basis. It's still not on a per part basis, but we're moving in the right direction. So to get it to a part basis, what I do is I take the equipment cost for productive time, which is this term, and I multiply it by productive time divided by a part. So it's how much time does it take to produce one part? And depending on the machine and the part size, we can calculate that. It's a thing that can be counted. As a matter of fact, what this is actually it's 1 over N dot, where N dot is the production rate. A very common term in manufacture is how many parts per hour do we produce. Or in the case of additive manufacturing, maybe it's how many parts per week can we produce, right? Because additive tends to be fairly slow and they have fairly low production rates. So at any rate, so I come up with this term here, which has the equipment cost, which I know, the write-off time, which I know, the load, which I know, and the production rate, which I know. So I can actually, for a gun run, I can sit and calculate the fraction of what the fraction of the equipment cost is on a per part basis. So this becomes the equipment part of the equation. And so, by the way, we can see here fairly simply what I mentioned earlier today, which is if we want to get the cost down, the two, we can by analyzing this, we can see what I guess operators already know is if I want to drive this down, the easiest way to do it is to reduce the equipment cost to produce cheaper machines, or to increase the production rate. And those are the two primary areas that we attack in order to get this down. You could also increase the write-off time, go to 10 years instead of 5 years, right? And that will drive this down. And I could also increase the load, and that way I get more parts out in a year, which would also help with the economics. Okay, so that's this term. That's the second term. The third one is the tooling cost. Again, I'm not going to really belabor this too much because with additive we typically don't have a tooling cost. But just for completeness, what we do is, again, I have to write the tooling cost entirely off a given production run, right? So in this case, I take the tooling cost, C sub T, and the number of parts that I want to make with that tool, and this will give me the tooling cost per part, right? Very simple. But there's one sort of glitch in this, and that is if we have a large production run, which typically is not the case for additive, but if I have a large production run, it turns out I may wear out the tool, right? The tool may only be good for 500,000 parts, and then I have to replace the tool. And I'll have to do that if my production run is large, like 5 million parts I want to make. I may need 10 tool sets to complete that process. So the way that we incorporate that into the equation is I have an N sub T is the tool line, the number of parts that I get out of the tool. And what I can do is basically I have to determine based on the part count for my production run, I have to determine how many tools I need and multiply by that. Multiply this number by the number of tools that I need. For small runs, it's always one tool, so I'm going to have no problem. But the way we can incorporate is we can use this computer programming term, the ceiling function, which is if I take the total number of parts I need and the life of the tool, divide it out to get a number, and then what I do is I round up to the nearest integer. Because, for example, if I have, just to make the math simple, suppose I want to make 4,500 parts, and my tool lasts for 1,000 parts, then what I would have here is I would have 4,500 divided by 1,000 is 4.5. But if I want to complete the run, I'm going to need 5 sets of tools, right? Because I need four sets will wear out, and the 5th set will be half worn out, right? So I still have to have that 5th set to do the run, to complete the job. And I'm not allowed to pay for half of a tool set. I can't rationalize with people, well, look, I'm only going to use half of the tool line, so I should only pay for half of the tool. Right? It doesn't work that way. You got to pay for the whole tool to write it off. So that's the way this works. So then we have finally the tooling cost per part is the cost of the tooling divided by the production run. Then we have this term in here to take care of the fact that we may need more than one set of tools. Obviously, if my production run number is less than the tool line, I only need one set, and this would be a number less than 1, and then we would of course round up to 1. Okay, so here the overhead cost is the last of the terms that we have, and the overhead cost, it's everything else that has to be paid. It's not directly associated with part production. So here's some examples: the building rent, the internet, operator wages, the sales force, the office equipment, the air conditioner, the heater. All of these things cost money. And the only way I can get money to pay for those in a company setting is by burdening the parts I produce with more money to make them more expensive, to generate more income so that I can afford all these things. And so it turns out that there's really two types of overhead costs. One is overhead costs that stops when I stop making parts. The other is overhead cost that continues whether I'm making parts or not. And so if we look at this example here, the building rent is going to happen whether I'm making parts or not. I'm going to have to pay this. So this is based on total time. The internet probably is based on total time as well, because I can't go to my internet service provider and say, look, we're only going to be using it 8 hours a day, so I only want to pay for 8 hours and not 24. The company, the internet service provider doesn't care whether you're there or not. They're going to provide the service on a monthly basis, which will be total clicks to the clock. Operator wages, on the other hand, if they're an hourly employee, which they typically are, when they punch out at the end of the day when the machine stops, we stop paying them, right? We only pay them while they're working. And so this would be based on the productive time, what the cost is. The sales force, the office equipment, these typically HVAC, these are typically based on total time. But anyway, so that's the way it goes. So we have basically which bucket I put the cost into for overhead depends on whether the cost stops when the machine stops running parts or not. And so what we have is we basically have for the overhead cost, there's an overhead cost rate. This is a rate, it's so many dollars per hour times the total time, where this would be all of the cost, the overhead cost factors that continue no matter what, whether the machine's running or not. And then I also have an overhead cost rate, so many dollars per hour, multiplied by the productive time. And so this term goes to zero when we stop working. And so again, what I can do is, it turns out that we have this load factor, so my total time is the productive time over L, so I can substitute out here and convert this to productive time, which will help me get to a per part basis. And I have my load factor here. Then finally, what I can do is, so I can write the overhead time divided by the productive time, gives me this relationship, so I just divide productive time over. So this is so many dollars per hour while the machine's running. And then I can, like I did earlier, by converting with the production rate, I can convert my productive time into the part. They have the overhead cost per part. This would be this equation, where I have the total overhead for productive, for non-productive time, total time, divided by the load, plus the cost rate for productive time, divide times 1 over the bill divided by production rate. So again, if I want to drop this, then one way to do it is to make more parts, right? Quicker, to increase the production rate. So anyway, so here we are. So basically, I went through all these four. So what we can do is we can basically come up with the cost per part. This is the manufacturing cost. And this doesn't include any kind of profit margin or business effect. This is just basically what's it cost to build this part. And what we wind up with is I just substitute in the equations that I have here, and we have these following variables that go into this equation. And we basically can run this equation for a given scenario to calculate what the part cost will be. And I split up the variables in this equation into basically their variables associated with the machine or the fabricator. The scrap fraction, the cost of the equipment, the production rate, the tooling cost, and the tooling life. All of those are things that we typically, if we're in business, we don't really control those, right? I mean, we can control which piece of equipment we buy. But once I decide to buy an piece of equipment, these things are all pretty well set, right? Then there's the material variables, the material cost and the density. Again, if I pick Ti-6-4, this is pretty well decided for me what those parameters are. But then we have these other choices over here that are kind of really are business decisions, to be honest with you. The part volume is maybe determined by the designer or by what the customer wants. The number of parts would be, again, in a service bureau setting would be defined by the customer. They would come and say, we need 500 parts, right? The write-off time is a business decision. We could have, again, 5 years, 10 years, 15 years. That's something we would decide. The load is also a business decision. Do we want to run a 40-hour week? Do we want to have 2 shifts so that we can do 80 hours a week, run 3 shifts and do 24 times 7? That's basically this is kind of a business decision. And then we, of course, have the various overhead terms. So, how much we pay the operator, whether we have a receptionist or not, whether we have office furniture that's really nice or really cheap. Those are all decisions that impact these. And again, it's choices that typically we have. We don't really have a choice on what the density of titanium is, right? And we typically don't have much of a choice over here either. Okay, so let's look at these. So here's, I mentioned that I was going to tell you what the feedstock costs are. So these are the metals, and I just accumulated these from a certain from various sources. And what we see is that I show the dollars per kilogram, which is piece of N, right here, this column. And we can see that, for powders, a variety of powders, we're talking, sort of $40 per kilogram, up to as much as, $350 per kilogram for certain materials. So the titanium alloys, as we see, are pretty expensive. Inconel's cheaper, Margin steel's cheaper. The stainless is even cheaper, and then the aluminum are pretty cheap as well. And I think this is for powder. For wire, what it is, you can see one of the advantages for wire is it's typically cheaper on a per kilogram basis than the polymers. So we have typically here Ti-6-4, while in powder form we're talking $250 to $360. The wire form comes down to about $100 per kilogram. Then we have the other materials as well. I forget what ER70 is. It's $4 a pound. I'm speculating maybe it's a stainless steel. The powder cost I got from last year's Wohlers report. So the data's pretty fresh. The wire data I got from Martina Filomeno. He, I forget where he is now, but he was a principal in a wire-based headed manufacturing company. So I just called him up, I emailed him and said, hey, give me some ballpark values for wire costs. So that's where these came from. And you can see that basically in here, just to remind you, aluminum, Inconel, the nickel-based alloys, stainless steel, and titanium are really pretty much, at least to a first order, are being used relatively equally by service bureaus around the world. So we have that as well. And if you look at it, again, it's driven by the demand, obviously not by the part cost, because aluminum and stainless run about maybe a third or more or a quarter of the cost of the titanium, but yet they're used in equal amounts. Okay, so let's just use some examples here and exercise the equation. So what I did first, the first one is let's run it for a 5 kilogram titanium 6-4 part. So again, this is hypothetical, so some of the numbers are sort of made up, but clearly in a commercial setting, we would have more guidance of what these numbers are. So for a machine, for DED, I picked a scrap rate of 0.1. Again, let's say we're recycling the powder and sending out the satellites. Maybe we lose a little powder there. Maybe some powder winds up on the floor and gets swept up by the custodian at night. So there are places where we can lose parts. So I just put 0.1 here. I picked $500,000 US for the equipment cost. For a 5 kilogram part, I said maybe we can make 1 part a day. It seems like a reasonable number. The tooling cost is 0, because there is no tooling. And the tool life you don't worry about either, obviously, because there's no tool. On the material side, the material costs $60 a pound, and the density is probably per kilogram. The density 4.5 grams per cc. That's what that game is. And then I also picked these values. I think the part volume, based on 5 kilograms, we can calculate the volume of the part, knowing the density. And so it comes out to be 1,010 cubic centimeters. The number of parts we need, it doesn't really matter. I picked the 5 for write-off, and also picked the 40-hour work week. And then for the overhead parts, for each of these terms, I just picked $50 an hour for that, just for the illustration purposes. I think probably in a real setting it would be maybe twice that or more. Okay, so what we do is when we plug all these into the cost equation, it turns out that we're talking for this 5 kilogram part, the cost comes in at about $1,000 per part. And again, you know, the question is there enough demand to justify that? And maybe there is, maybe there's not. But this is the stage where sort of the value of doing the cost modeling comes in. Because what we can say is we can go, heck, that's awfully expensive. What can I do to lower the cost? You know, so we can play that kind of game as well here. So for example, if I show this table here, what it shows is the quantity. Basically, this is the table where the x-axis quantity is the first column, and the part cost is this is the second column here. Oh, actually, I'm sorry. I said it looks like it's this is wrong. This should be $10,000. Let's see. Let me see if I make sure I'm doing it right. I may have the wrong plot. Yeah, it's I'm off by an order of magnitude here. The part cost comes in at $8,000, not 800. But basically, what we can look at. So yeah, so we have to multiply this number by 10. But what we see here is that total cost per piece runs about $8,000 no matter what. The material cost is about 9% of the total cost. And so, given that, it's like, why would we want to fiddle around with the material cost? Because we only save 9%, even if I drove the material cost down to 0. And of course, the tooling cost is 0. The equipment cost comes in at about 14%. And in this case, it's the overhead is where the big expense is. So basically, if the low line through here, if I want to bring this down from $8,000, what I really want to address is trying to reduce the overhead. That's where we want to go. Now, there's another aspect that we can do, and that we can look at repair. So I want to talk about repair a little bit. So suppose we have a part that we've already built, invented. If somebody comes back, if we want to repair that part, it can be actually a lot cheaper. This really comes as no big surprise, right? Because the motivation for doing repair versus part replacement, it's clear that it's going to be cheaper, right, than throwing the part away and getting a new part, which is the reason we worry about repair. So in this case, with the cost model, what we wind up with is for repair, what I have is everything stays the same, except my production rate goes up because I'm depositing less material, so I can build the part quicker. So I use, just as an example here, let's say I do, instead of doing 1 part per day, suppose we can do 10 parts per day, because I may be only replacing 1/10 of the material. That's sort of the logic here. So my part volume then goes way down from, I think it was around 1,000 cubic centimeters down to 100 or so. Everything else stays exactly the same. And what I wind up with now is I drop the part cost down to $800. I reduce the cost by an order of magnitude by doing repair rather than building a new part. So that's the way the relationships work. So let's look at there's some case studies that I pulled out of the literature. Let's look at some of these. Again, it's reasonable to assume that probably they're not using the same cost model, but they still work. Yeah.
In the previous slide.
Yes.
So there is no mention of maintenance cost during the ideal time of the.
There's no mention of
maintenance cost.
Oh yeah, the maintenance cost.
Is it in overhead cost?
Yeah, right. So this would be like the custodian coming in at night. Is that the maintenance you're talking about, or maintaining the equipment?
Yes.
Yeah. It turns out that all of it rolls into the overhead. Yeah, it all appears in here. And so if it's a high maintenance operation, then we increase the overhead. Right. Yeah. So anyway, so here's a case study. This is a stainless steel part. It was a 190 part run. It comes from Germany. And in this case, what they listed in their article was the following. They're going to use the machine 4,500 hours a year, which basically translated into the cost model I presented is the production rate. It turns into NDOT. He converts into that. The depreciation is the write-off time to years. The investment is 500,000 euros. And by the way, this is a powder bed example, SLM. The material cost, 89 euros a kilogram. Part volume is 1 cubic centimeter, so it's a relatively small part. And this is the shape of the part here. The linear thickness was given. And so what we have is in their cost model, they showed this, where 3/4 of the cost is actually the building cost. And again, that's not too dissimilar from what I discussed at the beginning, where the build cost is typically about 60% of the total cost to make the part. And so then they have these other things that they include in their model. So there's a little bit for preparation cost, the building process, fixtures, the oven, where I guess they do a stress relief. And then they have the material cost in there, post-processing and machine cost. So so here the preponderance of the cost is the machine cost. And when they did their calculation, they came up with about 10 euros, maybe $11 for this part. So that's the analysis. Now, if I use my model that I presented and sort of substituted in the appropriate parameters, I come up with about $20, which is not too bad, all things considered, with the analysis. So again, we can sort of confirm or validate the model with this example. So here we are. I guess to sort of finish this up, then we have this cost model, the manufacturing cost. Again, the important thing to remember is that it's about 1.6. The total cost is about 1.6 times the build cost. And that seems to cut across virtually all of additive manufacturing. The manufacturing cost on a per part basis, it depends on material cost, tooling cost, equipment cost, and overhead. For DED, the metal parts, can cost anywhere from say $100 to $10K. I'd be interested if anybody has direct experience with this, just as a sanity check on that. But that's where we are with the cost. And again, it really depends on what the market will bear. $10,000 for a part seems awfully expensive, but you have to appreciate that the customer, if they only want 2 or 3 parts, if they go to a for example, a forging house, it can cost $40,000 for the part. So it depends on how badly the customer wants the part and what they're willing to pay and what the competition looks like. So anyway, what I mentioned is that typically with additive manufacturing, it's often the indirect cost of the equipment cost that dominate the part cost, and it's not the feedstock cost. Oddly enough, the place where if you play with the equations long enough, the place where the feedstock cost becomes important is if we're doing large volume builds. If I'm doing these small, 1, 2, 5 kilogram builds, the material cost is really a pretty small fraction of the total cost. Now, if I'm doing a 200 kilogram build, then it's a completely different picture, and the material cost can become very important. So, but sort of the takeaway from that is that generally speaking, just in broad sweeps and broad terms, the material cost typically is not the showstopper on the cost of the part. It's typically the equipment cost that drives the part cost. Anyway, so again, the factors that really impact the part cost are the build rate and capital equipment cost. And the feedstock cost is usually not too important. And again, this is the reason why when you look at additive manufacturing, that there's a lot of emphasis given to trying to reduce the cost of the equipment, and there's a lot of emphasis to increasing the production rate. And again, it's not because we're stingy or because we want to have more time for the weekend. It's because it directly impacts the cost of the part. show you examples of this. Examples of bringing the cost down, capital equipment cost. It motivates the indirect processing techniques for metals. You know, the binder jetting, the material jetting, and the material extrusion. Those are all relatively cheap machines compared to the fusion machines like DED or powder bed fusion. And the driver to develop those parts, you know, the X1, the direct metal, Mark Forge, those machines, the driving force is to reduce the equipment cost, to drive down the part cost, to be more competitive. And so that's the real driver there. The other, on the increasing the production rate, you know, there are a number of examples of this as well. In the metals world, perhaps one of the more common examples with the laser-based processes is using multiple lasers to increase the build rates. That's one example. In the polymer world, we have, you know, processes like HP's multi-jet fusion that, you know, where we're curing the entire layer at one point rather than rastering a laser beam, for example, so we can build faster and increases the production rate. Yeah, so those are the kinds of things. As a matter of fact, actually, I'm in the process of starting to serve on a dissertation for a student at Georgia Tech, and he's working on a new technique. Actually, the Carolyn Seepersod, his advisor, had developed in Texas before she moved to Georgia Tech, and this is called RFAM. It's radio frequency additive manufacturing. So what's done in this case is the build is sort of like a binder jetting process, where we take a metal powder bed, or I guess in his case, I guess he's working with powder, with polymers, so he works with nylon. So you take a nylon powder bed, spread nylon powder, and then shoot down a dopant, which typically is carbon black, which is highly couples to radio frequencies. It gets really hot, but they shoot down the dopant, say the carbon black, at various locations where the part is. This happens very quickly. It's a very fast process. And then they remove the part out of the chamber, and then they bathe it in radio frequency light. And what happens is the dopant, the carbon black, gets really hot and will actually melt the powder together. So there's a lot of questions I have about this process, but again, the entire motivation for that process drives back to this case of trying to increase the build rate in order to drive the part costs down. Okay, that's enough of that. So we have finally I have repairing a part results in large cost savings compared to part replacement. Again, it's largely to the increased build rate. I can produce more parts because I'm replacing a small volume of the part. If I build at a constant volume rate, which is what we almost always do, so many cubic centimeters per hour, I can build more parts, which means my end dot goes up, which means all the costs go down. So it's as simple as that. And I think that takes me to the end of the presentation. If by your leave, we have to think about 15, 20 minutes. If I could, in terms of what the market will bear, if I could, I'd like to tell you a story about that. It deals with me sort of being a wisecracker or trying to be silly with some people. It turns out that in 2009, it was an interesting year. It was a year that I've already talked about this once. David Rosen and Ming Liu organized this road mapping study for additive manufacturing. It was funded by the U.S. Navy and by the National Science Foundation. And we met about, I don't know, maybe 100 people in Washington, D.C. for a few days to talk about where the challenges were. And so completely aside from that context, and one of the coffee breaks, there are 5 or 6 of us standing around and chatting. And what we were chatting about was a brand new additive manufacturing machine that had just hit the market, and it was produced by EOS. It was a polymer powder bed fusion machine that was specifically designed for doing peak powder, polyether ether ketone material. It's a very popular material for example, it has a lot of applications in biomedical as well as other places. It's a very hardy material, but it's relatively difficult to process. And as I mentioned before, with peak powder at the time, it turns out that to charge the chamber, it was literally $40,000 of feedstock cost, as I mentioned earlier, and you only use about 20% of that powder. About $8,000 goes into the part. $32,000 you throw in the trash can because peak powder degrades thermally so rapidly that it cannot be recycled at all. So it also has application in aerospace. So here's the story. So we're standing at the coffee break, and one of the people sort of rehearses for us what I just told you about the cost structure. And I was sitting next to a person who worked in aerospace, who worked for Northrop Grumman in California. And so just in order to try to get a rush out of my friend from the aerospace company, I sort of exclaimed at the end, I said, heck, that's it. That's even too expensive. It's even too expensive for aerospace to use. And so, you know, the aerospace, excuse me, get some water. Aerospace in the United States has a reputation for being really expensive. You know, the very high cost tolerance. And so I was basically giving my friend a hard time because of the aerospace content, you know, by saying that it was too expensive for aerospace. And what happened is everyone in the circle, you know, sort of giggled and chuckled at that thought. And but then the footnote to this is immediately after the laughter quieted down, he leaned over and whispered into my ear and said, "No, it's not," because even at that cost factor, aerospace was still willing to use it. And so, you know, we're talking extremely expensive parts that, you know, a kilogram part might be several $1,000s in polymer, but yet in aerospace they have the demand and they have the cost justification to do it. So just because it's expensive doesn't mean that it won't work. I guess is sort of my bottom line on that stage. So with that, again, I guess we can open to questions and discussion. I think we have 15 minutes left. Yeah, the cost factors for those. Yes. Yeah, I'm not really sure. I haven't priced out the DED machines for cost. I mean, I can speculate. I don't know. Do you guys know? I mean, what the cost? Which are cheap? Which are more expensive?
I think.
Which is the cheapest?
I think when comparing
wire-based with EV.
Yeah.
So electron beam wire, the expert says is the cheapest.
I think when comparing laser and electron beam, where are the manufacturing has the higher cost efficiency? To my knowledge, I think.
Yeah, sure.
Because in wire it uses the conventional welding center.
Right.
And also there's a high deposition rate.
Right.
And large scale common maybe also.
Right. Yeah, yeah, you bring up a good point. When we get to the case studies later this week, particularly for repair, what we find is apparently the way that a number of companies have gone is there's sort of one of two approaches. The common approach is for a machining company, a subtractive company, to take a additive head and to attach it to their subtractive machine, I guess with hybrids, and so that you're not really buying the entire machine, you're just buying the head. And I think that's, I think that may be with art. That may be
from machines with respect to hybrid additive manufacturing. laser additive as well as they were going to machine in the same process. That's what hybrid is going to be most cheaper. Instead of arc, they are trying to use the laser with the wire, and then they can able to fabricate it and they can able to machine. That can be a cheapest way they are trying to do.
Yeah, I
Some
think
case
that,
studies are there, maybe this week is going to explain.
right. You know, the laser, I mean, I'm assuming that we're talking 250, 500 watt type lasers. You know, those are, you know, quite expensive. So I think that it wouldn't surprise me if the laser process is maybe the most expensive for the equipment. I haven't really priced the equipment lately, not even the powder bit stuff. I'm not really sure, you know, where those costs are coming in. I'm throwing around numbers like, you know, $500,000 for the equipment. And I know I've seen reports of new equipment that rolls out that can be as much as $1 million. Maybe, I mean, some of you may be familiar, may even be more expensive equipment than that for additive that are, you know, large platform equipment. I think easily can run over $1 million. So, yeah, they can be expensive. Goes the opposite direction from what we want. So, yeah. Anything else?
Sir, is there any composite structures applications which is building by the DED methods
Is there any?
in aerospace particularly?
I heard most of that. I'm sorry.
Sir,
didn't I-
with the help of DED, we can make multi-materials and other composite structures in basically in aerospace.
Right. Yeah, multiple
yeah.
materials
Yes,
for aerospace.
so is it expensive? Because in other processes it is like complicated, but in DED very less applications are there.
Yeah. Unfortunately, my ears are too bad to understand. But would you, if you put the mic down and just shout out, maybe that will help.
Yes, sir.
Because I think the mic is distorting the sound.
Sir, my question is about the composite structures that we are making from the DED process.
Uh-huh.
So is it costly or not, sir?
We're talking about multiple materials
Yes, sir.
and the cost.
Yes, sir.
Basically, yeah. Thanks, Dan. I'm sorry for the issues. Yeah, with obviously there is a cost factor with doing multiple materials, and again, the classic case in point is with DED. But the cost factor is going to be with producing multiple heads, typically for powder. Again, typically it's powder deposition. So there's that, and then I suppose there's some control issues because you have to be able to with a multiple material machine, you have to be able to know when to turn the various nozzles on and off. So there could be a cost factor associated with that. I don't think there really would be sizable other costs associated with doing multiple material fabrication. I think the cost factor is probably overall. I mean, I could imagine. I wildly speculate that maybe there could be maybe a 10% increase in the cost of a machine to do.
Because mixing of two materials is also a challenge.
Right, exactly.
Maximum.
Yeah. And so if there's more done than simply squirting down different powders into the stream, that there are mixers involved between the powder components and the machine. Yeah, then of course that would be another cost factor. Right. That's your absolutely right.
I have a very primitive, doubt. Could you explain what is the difference between remanufacturing, sustainable, and recycled?
Yeah, so you want the difference between
Remanufacturing.
e-manufacturing, sustainable manufacturing, and the third one was
Repair manufacturing,
repair manufacturing. Yeah.
sustainable manufacturing, remanufacturing, and
Yeah.
recycling.
Right, or recycling, right. Sure. Yeah, I wish I could, but I can't. Unfortunately, maybe Lisa, maybe you want to take a jab? Because I don't really work in those areas to have the, or read the, maybe,
So
you can address
remanufacturing, you can able to do some part is worn out. You can able to repair with your remanufacturing process. But sustainable manufacturing is how you can make use of the resources by minimizing the wastages. That's what we can say sustainability. But even we cannot say the additive is completely sustainable or not, comparing with your conventional manufacturing process. Because in some aspects we can say it is sustainable. But when you say the wastage of powders, and what about the cost of manufacturing with respect to the part comparing with the conventional manufacturing? If it is a cost of, if you want to make a huge number of parts, this is not sustainable.
Okay.
In those aspects you can consider. But remanufacturing, again it is like a repairing of parts. If there is any parts already existing, if it is damaged, if it is worn out, we cannot able to repair with your conventional manufacturing process. But with additive manufacturing, especially with the DED, we can able to repair it. We cannot able to repair with your laser powder bed fusion, but because we cannot able to put your part into the powder bed.
So in this point of view, are we applying the process in manufacturing only or later the product also?
Yeah, even later the product also. We can make clear net shape parts as well as we can repair the parts, as well as we can add some kind of additional features onto the part. That's also possible with the.
So in a way it is involved with recycling.
Yes.
Thank you.